How, are you recovering from your jet lag with all your travels?
A little bit, yeah. Thanks for asking.
Yeah,
Uh, you're in Florida, is that right?
that's right. I'm just down the road from Jim Whitescarver.
Oh, very good, very good.
Yeah, we've got a healthy population of people interested in our chain here in the Tampa Bay area.
That's great. That's really
Yeah,
good.
yep.
Let's see. So I have some updates. Kent, do you want to give some updates?
Yes. So I guess mostly, or if possible, I would like to show the new validator incentive stock.
Sure.
Okay. Um, can I share my screen?
Yeah, go ahead.
Okay. So this is the doc. I think we've seen this many times, but so I guess I'll just start reading if that's okay with you.
Sure.
Okay. The proof of stake contract is a Genesis contract written in Golang. It defines a set of methods that codify how validator incentives will work. Validators can propose non-empty blocks at any time they wish. The active set of validators are defined in the bonds map of the proof of stake contract. The bonds map consists of up to a constant key value pairs where the key is a validator's public key and the value is their corresponding stake denominated in revs. Bonding requests, which are calls to the bond method in the proof of stake contract, are submitted through transactions to the network. Bonding requests insert the validator that initiated the transaction along with their stake into a draw map, which has the same structure as the bonds map, but is unlimited in size. Every epoch, every constant number of blocks, as many requests are stake weight randomly selected from the draw map to fill up the bonds map. If the bonds map is currently full, then a constant of the bonds map is swapped out with the draw map using a random seed in the block. There are no joining fees. Transaction fees from the processed transactions are split stake weighted to the rewards map in the proof of stake contract. The rewards map is similar in structure to the draw map, but instead of holding stakes, the reward map holds the accumulated share of transaction fees denominated in revs. Every seniorage blocks a constant percentage of each validator stake will be transferred from the co-op's wallet to the corresponding validator slot in the rewards map. Unbonding requests, which are calls to the unbond method in the proof of stake contract, are submitted through transactions to the network. The validator corresponding to the deployer of the unbonding request is removed from both the bonds map and the rewards map. If a validator doesn't have a block in the past constant number of blocks in the current chain, any user may submit a transaction to forcefully unbond them. The sum of the corresponding rev values in both maps are inserted into a withdraw map under the validator's public key. Long-range attack blocks after the insertion of an entry into the withdrawal map. Validators are sent their corresponding number of revs in the withdrawal map to their own wallets. Slashing invalid blocks or equivocations is done through transactions that call the slash method in the proof of stake contract. If the slashing attempt is valid, the validator stake in the bonds map is set to 0.
Mm-hmm.
Any comments or?
What's the punishment for an illegal slash?
Oh, the bonds map. So you lose your stake.
Okay, so if you illegally slash, you're slashed.
Yes.
Okay, cool. This looks about right. I see you really, really didn't want joining fees.
Oh
This is-
yes. Well, yeah. I mean that's from before.
yeah, exactly. No, but this looks about right. So I think this is pretty much everything that we've discussed, and it includes all those constants that are necessary to comply with IOB 5.
Cool. Good to hear.
Yeah, I think this. I'm not seeing. I'm just now. Like I want to get this in code and get HackerOne involved.
Hmm.
Because this would be exactly the target.
Cool.
Yeah, this is great. Thank you. Any questions, Jim, Steve, Christian?
No, I thought it was good. I followed along well. I'm going to probably listen to the recording again or read through it to get a better understanding, but it sounded good to me.
Cool.
Thanks.
I'll post the link in the chat.
That's good news.
Thanks.
No, it's, we know what the constants are, and we can determine their values, and I guess HackerOne is can help with that too.
Yeah, absolutely. Okay, I'm going to give a quick update on Rolang 1.1. So these are, we've decided none of these features will go in before mainnet, but will go in shortly after mainnet, like really shortly after mainnet. But I want people to be able to see what's coming down the pipe with respect to Rolang. So the first thing is a new and improved for comprehension. So the usual, this is the shape of a for comprehension, and what's different is just some minor syntactic thing. Instead of a semicolon here, we have an ampersand, and so so the old semicolon has been given a new makeover. It looks like an ampersand, and then we've repurposed semicolon to actually mean sequence. So you can have a bunch of things kind of joined together and then do more things joined together and then etc. So the semicolon is intuitively is going to mean nesting of for comprehensions, and this is going to be the join for the tuple space semantics. The other change is again, it's syntactic sugar, but instead of just having a channel here in the source position of the assignment arrow, we have three things. So it can either be a channel, or it can be a channel decorated with a whimper and a bang, or it could be a channel decorated with a bang and a whimper followed by some arguments. So I can give some intuitive meanings to those. So intuitively, if you have a whimper and a bang, it means you're listening, and then you're going to send an acknowledgement that you got whatever you got on that channel. So the pattern here is going to be augmented with some sugar, which allows you to match against the pattern and the return channel. So you don't have to worry about all of the programmer does not have to worry about the return channel structure in the pattern or anything like that. That'll all be conned up by the compiler. So you can see that's what the translation of this form looks like. So if you have this form here, then that you take the pattern and you turn it into a bigger pattern, which is expecting the return channel, and then after you've gotten the data and the return channel, then in the body of the for comprehension, in addition to running whatever the translation of P is, that's over here, you also send on the return channel just an acknowledgement. So no data or nil is sent on the return channel. And when we see the other side, we'll see that the other side is expecting an acknowledgement of the return channel before it releases its continuation. So again, if you just look, it's whimper, listen, and then send. So that's what happens. We listen, and then we send. Okay, and that's basically just a mnemonic for the meaning of this syntactic sugar. And then similarly, this is kind of like method call semantics. So here we're going to send, and then we'll listen. So we're sending something, and then we'll wait for the arguments before proceeding. So this de-sugars this way. So we create a fresh channel, and we send this argument list along with the channel down the pipe, and then in parallel, we listen on the fresh channel for the pattern. So that's this pattern here, and then we run the translation of P. So if you were to run this in parallel with something that was expecting a method call and was going to acknowledge or send the value of the method call back down the return channel, this would work perfectly in tandem with that. So these two forms are giving us a notion of synchrony in the syntax. So it's right now Rolang is all asynchronous, and this gives us some synchronous calls, which are very, very useful. And probably if you're following along, you kind of get what we're doing here. You'll notice that these return channel constructs don't actually have to hit the tuple space. It's not a requirement, so it's not only that we get some compression in code, but we'll also get some significant performance improvement. So here, let's just take a look again. Here's the general shape. I've called out the bang and then whimper, the sort of method call form in the first sequence chunk. And so essentially what we've done is we've de-sugared that and replaced the X with the new R. And so if you think about it, we'll kind of run this over and over again until we replace all of these things with just R's, right? There won't be any of the special patterns. They'll just be channels. Likewise, for these things, right? We'll get rid of all these and turn them into channels as well. So we run this sort of this a recursive pattern. We'll run this translation over and over again until there's nothing but channels on the right-hand side of the assignment form. And then the next step is that we, once we've got one of these, we can eagerly or lazily, depending on how we write the compiler, get rid of this as the remaining body as a nested for comprehension. So this will guarantee that this happens before the next one happens. So all of this happens first, and then this happens. So that's the nested for. So you can see that this would result in a significant blow up in the code if you were to write this by hand, right? In fact, both of them result in all three things result in a significant blow up in the code. So, or run the other way, when programmers use these syntactic forms, they get a significant compression in their code. And I'll give an example in just a minute. So on the output side, we have sequential output, right? So you can sequence an output before a continuation, which means that the continuation will not fire until you've seen an acknowledgement that the other side has seen the data. So you've got a receipt that the other side saw the data. And we just sort of get rid of trailing zeros. Instead of having to write semicolon 0 at the end of a long line of these, you just put a dot, right? So that also is a little bit of a code compression thing. So intuitively, what we'll do is we'll create a fresh return channel, a fresh acknowledgement channel, and we'll send that down the pipe, and then we hang this thing off of a for comprehension. So that's it, and that's exactly what we do, right? We have a, sorry, just gonna, there we go. So we have the translation of this is you create a fresh return channel, you send the data and the return channel down as a pair, and you wait on the return channel for the acknowledgement, and then you run the translation of P. And then desugaring the dot is just, putting a semicolon and a zero there. So that's that bit. And now let's take a look at what this does in terms of an example, right? So if I do a hey, right, a whimper and a bang, and then so I'm getting M off of one of those and N off of one of those, and then having gotten an M and an N, I write M plus N out to the stood out. And I run that in parallel with this thing, which is sending a 1 and then sending a 2. And we don't send the 2 until we know that the 1 has been received, and then we stop. So that one-liner expands out to at least a 2-liner. If you're writing this in even prettier Rolang, this would probably be about 5 lines. Minimum 5 lines of Rolang, so that it would be readable. But essentially what we do is, this expands to a pair, and when we receive this, we send back down on it, so that allows us to unlock this one, and this one expands to a pair. So notice this inline thing here becomes a nested for here. And then we also send that out on the R2 channel, and then we run the continuation. And that is run in parallel with the other side of this, right? Which is create the fresh return channel, send the data paired up with the return channel, wait on something from the return channel. We don't care what we get back, because all we want to do is just go forward. And then the next level down, that's the Y level, we create another return channel, and we send the data together with that return channel down the pipe, and we wait on that return channel, and then we stop. And now if you notice that we can kind of rewrite this in a nice way, a slightly nicer way, in 2 steps. And so by the second step, we've extruded the R1, R2 scope outward here, and that is what enables us to have these two communicate, and then they communicate, and the first COM event is on X, and it's guaranteed that it will be X. It can't be anything else. And it creates the substitution of @1 for M and @star R1 for R1, which is just the identity solution, because @star just becomes R1. So it's R1 for R1. I've kind of cheated here. To do the extrusion, I'd have to move these to one side, but it doesn't really matter because they'll be bound at the COM events. So I just left it. And then, so since the X has been communicated on, we unlock the R1 bang. So that goes out, and so that's the next COM event is these two here, right? And that leaves this one. And again, so these two can communicate, and that's this COM event here. Again, it's basically R2 for R2 and @2 for N, and which unlocks the R2 send, which is going to hit the R2 wait. So there's that COM event, and that leaves this. And if we get rid of the par 0 and we garbage collect a new, which doesn't have there's no mention of R1 and R2 in this final thing, right? So we can just garbage collect that away, and so that's that. And that garbage collection of R1 and R2 is related to the fact that we never have to hit the tuple space for R1 and R2. So you can see that this guarantees, if we filter out all the unforgeable name communications, it guarantees an event log of this COM event happening before that one. So that's the synchrony that's happening as a result of these syntactic improvements. So there's one other pair of syntactic improvements, but let me just check and see if there are any questions on that. Okay. So notice that you get a better than 2x compression on the example. So the code compression is quite considerable. So there's lots and lots of code throughout our sort of system contracts that use features like this, and they'll be able to get a lot smaller using this. And then if you take the two together, as I said, all the stuff where there's no observable transactional import, that can be done without hitting the tuple space. So it's not just that you get better than 2x compression, we also get at least a 50%, if not considerably greater performance improvement on the execution of Erlang. And likewise, we have a similar kind of thing going on here. So I think a lot of people have bemoaned the fact that it's hard to just, create some variable bindings in Erlang. So there are two forms of let expressions. One is the sequential let, one is the simultaneous let. And they provide sort of something that's equivalent to the Scala val expression. And so the desugaring of the let expression is we create a new channel where we're going to send the value. We listen for that value use the binding with that pattern there, and then we nest, right? So the next one in the pattern, we descend like this, and so this will turn into a bunch of nested listens together with some sends. And the other one, this will be a bunch of simultaneous sends and one big join. Right, so that's the semantics. Now, under the covers, we don't have to do either of those things because we never have to hit the tuple space. So again, this gives us clearly significant compression, especially in the sequential case. And we don't have to hit the tuple space, so it will give a dramatic improvement in terms of performance. So those are some basic features that will roll out in the not too distant future. We might even have prototypes before mainnet, but they won't be they won't be allowed to be blocking the core features that we're working on. Does that make any sense? People follow along?
Thank you. Sounded good.
That was
Cool.
awesome. I was just been lamenting that Erlang didn't have really a sequential mechanism, and I've been toying in my mind about how this might be done. Now you've done it. It's awesome.
Cool. Yeah. Well, I've just been trying. The thing is, Artur and I had this conversation. Like, whenever you give somebody something that is familiar to them, then they'll use that to. It's like a double-edged sword. I learned this the hard way with BizTalk, where I gave some syntactic sugar kind of stuff so that programmers could program in their old style. And they just did that instead of using any of the concurrency features. And it was very, very sad.
Well, a number of people have said, how do we stop this? Keep indenting more and more.
Yeah, exactly.
Curly braces. And
yep.
This kind of rolls it all up into one.
That's exactly right. Yeah. So there are lots of opportunities where the nesting is now just turned into inline stuff. So it should be much cleaner, much easier to read. Yeah. Vlad, you joined us. How's it going?
Hey, Greg. Sorry for being late. I was kind of in transit and couldn't really make it on until a little late. I'm well. How are you?
No worries. Good, good. We just gave 2 updates. Kent gave a nice update on our constants for the Casper POS contract, and then I just went over some improvements to Rolang that are coming down the pipe.
Cool. Yeah, I have a pretty cool update to give myself. Here, let me paste the link in the chat here. I have a fault tolerant, I think, kind of like proof or sketch proof of and the strategy for liveness in like a super synchronous kind of brown base setting. That kind of provides like a basic philosophy for or like approach for a liveness strategy. It basically has 2 parts to the strategy. The first one is called fault rejection, where basically if a validator ever fails to send a message to another, and as evidenced in the justification graph, they basically have to consider each other faulty. They both have to basically maintain the position that they're correct and the other guy's faulty, and they like never get to communicate directly again. And so there's ends up being this kind of communication graph, at least in the simplest version of the proof, that eventually has to become stable in an attack, because for an attack to happen, faulty nodes have to at some point stop showing new faults to correct those. Otherwise, they'll eventually run out of faults to show. So they have to get to a stable. They have to get to a stable kind of connectivity graph where validators, may see each other to be faulty, but some validators don't see each other to be faulty, and there's faulty nodes that are not observed to be faulty by some correct validators. And you can kind of take the graph of the validators, wherever like there's a connection between 2 validators if they're connected in the sense that they are sending and receiving messages for each other. And if they ever fail to send and receive a message to each other, then they become like disconnected. And so over time, this connectivity graph might kind of have fewer edges, but at some point, eventually it'll stabilize, and all the correct nodes will be in the same connected component to that graph, and they'll all see the same graph eventually. And so you can kind of use this connectivity graph for them to isolate a piece of the graph which is live, in the sense that if they all see messages from each other, they'll come to a decision, and then they just ignore that piece. And the classic one that we look at, the main one, the first one that I consider as a fully connected graph. So you have a set of validators, as the correct nodes are, that are fully connected. They're going to be live in these latest message majority-driven estimators. And so there's 2 parts of the strategy. One of them is just fault rejection that leads to this connectivity structure that eventually stabilizes. And then, assuming that there's like a limited amount of faults. And then from that connectivity structure, the correct nodes can find, can basically, anyone who's behaving correctly will have to produce messages in concert with a certain subgraph of the connectivity of the connected graph they're a part of. So every validator has to kind of play to their connected peers, and they need to send and receive messages from them, but they're not going to send and receive messages from all of them. They're only going to essentially look at a subset that corresponds to a subgraph that's live, because not all connectivity graphs are going to be live.
That's very interesting. You're using a similar strategy to the one that I propose, which is that you, by limiting the amount of error that you're willing to accept, it ends up turning into a communication constraint. So it's very similar to the error correcting code idea. You apply it in a slightly different way, but the core idea is by forcing a limitation on the errors. You are also forcing synchrony constraints. That's quite interesting.
Yeah, so I kind of do both separately. I have like synchrony constraints that are really strong, and I limit the errors. And eventually, like I plan on doing something a little weaker. But the idea here was just to get a proof that kind of has the property that doesn't have a fault tolerance threshold and is able to achieve the kind of network message passing overhead that we're thinking about. Although if you're looking for a fully text component, that is quite computationally difficult, and so looking at trying to find simpler things.
Sure, understood. You know, it's so interesting. I just stumbled yesterday. The number file guys give us a talk on error correcting codes and their spatial interpretation, which is very closely related to what I've been talking about. So it's a very, very strange to have those folks. So I just pasted a link, and then Vlad, I don't think you saw the talks that I gave, but they're up on RCast now. Where let me see if I can find the links. Hang on a second. Sorry, but it's cool. It's cool. I'm not a big fan of the round robin, but that's it's a good place to begin.
Yeah, so right now it's kind of assuming so the round robin actually in some way makes it a little bit easier than the case where everyone is making a message at every slot. So if everyone is always broadcasting a message all the time, like at every time in this case time slots.
Yeah.
Right. Yeah, and if everyone is broadcasting at every slot, then it's actually harder to have liveness, it seems, than with the round robin. But obviously neither are perfect or ideal at all.
Yeah, exactly. Understood. Okay, here we go. So RCast number 24, talks about the framework for programmable liveness. So I'll just paste that here. There you go. Yeah, cool. This is really good. I think we're converging, and it's really nice when we sort of come to similar, actually very similar conclusions independently. That gives me confidence that we're working towards that there's a one thing there that we're working towards with from different directions.
Yeah, I mean, liveness is very much a thing, I guess.
Yeah,
One thing that also kind of always comes up when I think about these liveness mechanisms is like you can use them optionally in the sense that every once in a while to force decisions if it's not decisions happening, and kind of have more of an optimistic approach where you're not using these more complicated strategies or more structured strategies until necessary in order to allow more arbitrary behavior.
Although theoretically you can bring it down to category theory, that in practice it's a complex, multi-dimensional, proven to be impossible to solve problem.
Well, Jim, the idea is that in order to get around FLP impossibility, you impose some synchrony constraints. I mean, the tricky bit, all you need to do is impose synchrony. And now the question is, where do you impose the synchrony, and how do you impose the synchrony? Those are kind of interesting and subtle questions. One of the biggest issues is if you're going to impose synchrony by everybody sharing a wall clock. So a common wall clock is a typical part of a solution to this problem. But wall clock time is really hard in a distributed setting. Network time.
I love the emergent time that
Yeah. That so that we just like I don't want to have to deal with that crap. Pardon my French, but that's like right out for me.
I'm looking, looking at it also from the point of view of we can never know that we've protected against all possible games.
Right. Yeah.
And that's why these three dimensions are important. They incorporate an aspect that is meaningful.
Yeah. Exactly. So cool, Vlad. This is really nice. Thanks for the link. I'm looking forward to reading it.
Yeah, it's pretty cool. The main kind of insight that really helped was that there are non-stable, non-faulty arrangements in a way that like there's no faults being shown, and it's still not live, and so there needs to be like an additional kind of mechanism in the strategy other than just rejecting peers for being faulty.
Yes. Yeah.
Which is thanks to Daniel Kane.
Is he the one that came up with the much cleaner safety oracle thing as well?
Yeah, that's right.
Yeah, cool. Very nice. Well, he should come to the Casper Hangouts. I haven't met him yet.
Yeah, he doesn't like to wake up before 11, I think.
Oh, is he West Coast?
He's West Coast, yeah. But but I'll ask.
Cool. Yeah. A lot of fun math happens before 11 a.m.
The idea of the validator cliques is could introduce the notion of locality, which is another thing that's been concerning to me in decentralizing our chain, and really eliminating honest mistakes where two validators calculate the next integer and they both get 1, but it's wrong. To have the idea of local channels and global channels, or a degree of locality. And I was thinking that could be pretty much invisible to the programmer. But I think that idea connects well with the idea of creating these cliques.
Yeah. So unless there are any other updates, I'm going to use the next 20 minutes to go grab a cup of coffee and some breakfast before I have to get to dev stand up. But I'm happy to hang out if there's more updates.
Thanks, Greg.
Thanks.
Yeah, cheers.
All right. Ciao, ciao.
Enjoy. Bye.